Welcome to Rawson Connection, a podcast about all things Lehigh engineering, coming to you from the P.C. Rawson College of Engineering and Applied Science at Lehigh University. It's a show for students, alumni, faculty, and staff, current, former, and future, and for anyone who's interested in the many creative ways that engineers are solving the world's problems. I'm your host and producer, Christine Fennessy. So, I have to walk down 2 flights of stairs from my home office to get to this basement closet where I record this podcast. And I'm lucky. None of those steps cause me any pain. But that is not the case for 31 million Americans who suffer from osteoarthritis. Osteoarthritis is the most common form of arthritis, and it occurs when the protective cartilage that cushions the ends of your bones wears down over time. Lesley Chow is really familiar with that breakdown. Lesley is the Frank Hook Assistant Professor in the Department of Bioengineering and the Department of Materials Science and Engineering. And earlier this year, she received a Faculty Early Career Development Program Award from the National Science Foundation. It's also called the Career Award. It supports the work that she and her team are doing to, in a nutshell, regenerate cartilage. I wrote a story about Lesley's research and her award for the fall issue of Resolve. The issue comes out this week, both in the mail and online. We wanted her to talk more about her research on the show because honestly, what she's doing is very cool. And it's super relatable because we've all got joints and a lot of us have pain. In this episode, Lesley talks about the role cartilage plays in the body, why injuries to it can be so devastating, and the novel approach that she and her team are taking that may someday help people avoid debilitating pain. Remind us what cartilage is exactly and why it's so important.
Yeah, so cartilage is a tissue that exists in your joints. And it plays a really important role in you being able to transfer load. So every time you move your joints, every time you take a step, your cartilage acts like a shock absorber so that your body can have pain-free movement.
Okay, great. And so how does it get damaged?
So it gets damaged rather easily, actually. So you can have damage due to, an athletic injury. You could, slip and fall, and it eventually gets damaged as you age as well. So it'll change over time. And the main issue is that it doesn't heal itself.
Okay, yeah. That was what I was going to ask next is, so why is the damaged cartilage a bad thing compared to, say, like breaking a bone?
Yeah, so your bones have a capacity to heal. So they have a natural capacity to regenerate themselves within reason, but that you can have a broken bone and not have any procedure done, and your bone can heal itself in a cast. Cartilage, on the other hand, doesn't have the same propensity to heal, meaning that it doesn't have blood vessels, it doesn't have nerves, and those are parts of your tissues that are typically involved in the healing process. So your bone has nerves, it has blood vessels, and it can bring cells in to help clean up the damage. Unfortunately, in cartilage, you don't have that same sort of a setup to have the healing process occur. And so once you have damage, it can reform tissue, but it's just not really what your original tissue was like.
Got it. Okay. And so when you say it can reform tissue, but it's not the same, what does that mean? Like, say, for example, I've damaged the cartilage in my knee. What might that mean for me, say, 10 or 20 years down the road?
Yeah, that's a great question. So your tissue, as all of your tissues are in your body, are very specifically organized so that the tissue can function the way that it needs to. So with cartilage, you have distinct zones within your tissue, and those zones are really important for you to be able to, what we talked about earlier, be able to take a step and have that load transfer to your bones without feeling pain. So your shock absorbers. So when you have damage occur, that tissue doesn't have the same organization. So typically your cartilage tissue that's in your joints is called articular cartilage. When that tissue becomes damaged and it has to regrow something, in the damaged area, it turns into something called fibrocartilage. And that cartilage is completely different in terms of function. So it's just not going to serve the same role that it needs to serve when it's in your joints.
So how does this then play a role into developing, say, osteoarthritis?
So once you have damage, your path to osteoarthritis is inevitable. Osteoarthritis is considered a disease that's a whole joint disease. So once you have damage to your cartilage, it leads to other pathologies that we're still understanding. We still don't really know what happens, and we don't know what are the key players. We're learning something new every day about the onset of osteoarthritis. And so once osteoarthritis starts, it's very difficult to stop, and it keeps progressing to the point where you lose your cartilage, and then eventually it starts damaging the bone beneath your cartilage, known as the subchondral bone.
And so is that when things like knee replacements become inevitable?
Yes. So your cartilage doesn't have nerves and vasculature, and that's actually by design. So when it's acting as your shock absorbers, you don't want to have nerves there because you don't want to feel the load and you want to transfer the load to your bones. But that same setup that, makes it so that cartilage doesn't regenerate, once it's damaged and it can't reform, we're then talking about the load now gets transferred directly to your bone, and that can be very painful. So when you have bone touching bone, you have nerve endings in your bones, and so therefore you feel every step that you take.
And so when you have a total knee replacement, how does that exactly eliminate the pain of osteoarthritis? Is it because you don't have the nerve endings in that prosthesis? Is that right?
Yes. So the pain that you experience with osteoarthritis is a total joint problem. So it's a total joint disease. So you have damage to your cartilage. It progresses and it begins damaging the underlying bone to the point where you lose mobility, and it's just so painful to even take a step. And so the only solution at that stage is to just remove the tissue completely. And so when they remove it, they completely resect out the joint and they replace it with an artificial joint that's typically made out of metals.
And so it's a good solution.
It works,
obviously, to a very painful. Right. Yes, but part of the issue that you're trying to solve is that this is also very expensive, and these things they don't last forever, right?
Yeah. So it is very. So I think maybe another way to think about it is that the onset of osteoarthritis is not well understood, and the progression of it is not. We know what happens. But once you reach a point where you really can't go back and try to repair, that's usually when the patient starts feeling the pain. And so what we're trying to do is intervene a lot earlier before the patient starts experiencing pain. People don't go to the doctor until they're debilitated or they're having issues. And when that's the case, then they're usually at a stage that's so late that the only solution will be wait as long as you can and then have a total knee replacement. And the issue with that, the reason why they wait as long as they can, is because the total knee replacement doesn't last forever. And so we're saying 10, 20 years, but if you're a patient that's in their 40s, that's not a reasonable time to have a replacement because you're going to outlive your implant. And so we worry about that because if somebody's going to outlive their implant, that means they have to have a replacement surgery. And that surgery is not going to go nearly as well as the first surgery. So we call those revision surgeries. And the reason why it doesn't go well is because you have tissue that's, it's undergone a lot of trauma. You've replaced it with a metallic implant. And then the bone that's surrounding and supporting that implant, usually when you have a replacement, it's because that tissue's been damaged. And so now you're trying to throw in another implant into tissue that's already damaged, and it just doesn't go as well.
How would I be treated today if I've damaged my cartilage very recently? How would I be treated today given our current understanding of regenerating this tissue?
Yeah, so there's certainly a number of different interventions that they can do surgically that are clinically done. So you could have a procedure like microfracture where they'll remove the damaged tissue and then they puncture into your underlying bone to get your bone marrow to come out. And that bone marrow has stem cells that can help regenerate the tissue. You can also have chondrocytes, which are cartilage cells from a different region of your tissue, usually a non-load bearing part of your tissue. They grow that up in culture outside of the body. and then you come in later and have those cells injected into your defect or your damaged tissue site. There are some biomaterials that they can implant. So there are a variety of different techniques depending on the severity of the injury, depending on, honestly, the surgeon and their preferences. But unfortunately, it all still produces that fibrocartilage that I mentioned before. It's producing a tissue, and I liken it to, like sticking gum on a leaking pipe. It's a solution, and it offsets the need for an implant, a total knee replacement, but it leaves you in the same situation of eventually needing additional interventions later. So that tissue's not going to respond the same way.
Okay. Now, this might be obvious given everything that you've just said, but I was just hoping that in a nutshell, before you describe your actual research, what is the problem that your specific research is trying to solve?
Yeah, so we're very interested in the fact that tissue is so organized. And we know that organization is very specifically related to its function. So it needs to be organized so that it can serve its role as that shock absorber. And when you disorganize it, it just can't do the job the same way that it needs to do the job. And so what we are trying to do is understand more about how that tissue regenerates, because it has a capacity to do so. It has a capacity to produce tissue. But what we don't understand is, why does it not produce tissue in the same organization that it was in the first time it formed? And so what we're trying to do is think about in all different ways, right? So we look to development in nature as an inspiration to help us understand, how does that tissue form in the first place when during the tissue's development. We're also looking at, what is it that the cells respond to? So what is it about our material that gets cells to do certain things? So we're kind of coming at it at different angles of, can we replicate what happens during development, that we can try to, reform that tissue the way that it was in the first place? Or could we just try to understand, what do the cells do when we give them different biochemical cues, when we give them different physical cues? What, sort of home can we give them to get them to do what we want them to do, with the idea of, spatially organizing that tissue again?
Can you just, for the layperson who might be listening to this, just explain briefly what you mean by organized tissue versus disorganized tissue?
Yeah, so each of your tissues in your body, so all the different tissues, your skin, your organs, like your kidney, your bones, your cartilage, all of these tissues are organized in very specific ways, meaning the different components that make up your tissues, they are placed in very specific places within that tissue. And if you take it, so the example that I like to give is, if I took your tissue and I put it in a blender, it would no longer function the same way, right? We can agree that for sure would not work. But you could argue that all the components are there. So why wouldn't it still function the same way? But that's because it had to be organized in a very specific way. So a good way to think of it is the way that a building is built. You have a certain structure that holds up that building. The building that our College of Health, our new College of Health building, the Health Science and Technology building, we saw from the ground up how that was being constructed. And it had to be constructed in a very specific way. So that gives us a great way of thinking about, you need, that physical structure. The materials are all placed in very specific locations. Otherwise, it's not going to be a building. And so this is the same idea with tissues. All of the different components that make up your tissues need to be specifically placed in a precise location. Otherwise, that tissue is going to respond differently. It's going to have different mechanical properties. It's going to have different chemical properties, and so on.
Okay, so now take us through your research. Help us understand what your lab is doing exactly to solve this problem.
The approach that we're taking is trying to construct a material that will help rebuild that tissue the way that it is originally. So respecting the organization of the tissue as it was formed after development. And so the approach that we're using is similar to the way that you would build a building. We have all of our different components that we need to construct the building, and then we're using 3D printing to control where those different components are going. And so this allows us to find out what is it about our material that can drive the formation of the tissue that's more similar to the native tissue. And then because we're taking this modular approach, we can mix and match the components, put them in the locations that we want them to be in, and sort of build that home for the cells in a way that we can really drive the formation of the tissue that we want to form.
Oh, okay. So is the idea that, you're building this platform, would you be implanting it?
Yes. So the idea is to make a material out of materials that can degrade. So we're using polymers that will degrade in the body. And then we're decorating the surface of these materials with biochemical cues that signal to cells. And the idea is you would take that material and you would implant it in the damaged tissue, and it would signal to the cells in the body, hey, you should maybe grow more tissue here. You should grow more cartilage here. You should grow more bone here. And we're trying to make something that you could implant that will help that tissue form in the way that it's supposed to form. So if you remember, I mentioned before how you could regrow tissue. It's just not organized in the way that it needs to be organized. And so we're trying to give it a little jump start. We're trying to say, okay, I know that you can do it, but I need you to do it in an organized way. So if we give it a home for all the cells to live in and to see their microenvironment, the goal is to have it so that the cells can infiltrate into the tissue or into the scaffold. And then that scaffold will tell the cells what to do, how to produce the tissue in the right way.
Okay, in terms of this idea of telling them what to do and giving them these cues, can you talk a little bit more about what you mean by the cues?
Yes, so these cells have a natural propensity to regrow that tissue and regrow that matrix. It's just, as I mentioned before, they don't know how to do it right. And so what we're trying to do is tell the cells that have the ability to differentiate into other cells. So you have stem cells that exist in your bone marrow. We're trying to get those specific cells, known as mesenchymal stem cells, to differentiate into the cells that produce cartilage, to the cells that produce bone, so that they can form that tissue that they need to form. We also are trying to signal to the cells that exist on the edges of the defect. So you already have cartilage cells, you already have bone cells that exist there. We're trying to get them to help regrow the tissue and support those stem cells that are infiltrating into the scaffold.
Okay. And so what's the nature of these cues that you're giving them?
We're providing biochemical cues that are replicating some of the biomolecules that exist in the native tissue. So our thought process behind that is that if we are providing the cues that they would normally be seeing, we're hoping that that gives them the signal that, oh, this is the type of environment I would see in cartilage, so I should turn into a cartilage cell. Or this is the type of environment that I would see if I were in bone tissue, I should turn into a bone cell. And so we're trying different chemical cues to get those cells to go down the path that we want them to go. So we are basing this off of our own group, our own experience with it, and other groups as well who have looked towards understanding how cells respond to these specific chemical cues. But the nice thing about our platform is that we can change the biochemical cue. So we can make it be something else if we're not seeing the response that we want. But the key thing is we have a strategy that enables us to control where each of those cues are within one single material that can be implanted.
And is that strategy because it's being 3D printed?
Yeah, so the combination of the molecules that we are synthesizing with the 3D printing all together enables us to control where multiple biochemical cues are going within one material. So the nice thing about that is that we don't have to, glue two different materials together. We don't have to do a lot of post-processing after we've made a material. We can just print one thing and implant that as is. But the 3D printing really enables us to really precisely, control where each cue is going to be. So the advancements with 3D printing have been really beneficial to us. And then combined with our technology of being able to synthesize materials that will present the different cues on the surface, that allows us to really create whatever material we want.
Wow. And so what is an example of the type of environment that cartilage tissue prefers? Like what would be the biochemical cue that would signal to a cell, hey, turn yourself into some cartilage?
Yeah, so the cartilage has a variety of different extracellular matrix molecules. So we call them ECM molecules. So these extracellular matrix molecules include things like collagen 2, proteoglycans that are very important for the load-bearing response, known as aggrecan, hyaluronic acid. All these different biomolecules exist within that cartilage and are known to push stem cells like mesenchymal stem cells towards differentiating into cartilage cells. Just seeing that in their local environment is known to push them towards that behavior. On the bone side, we have hydroxyapatite, which is a mineral. It's the primary mineral component in your bone, and as well as other types of collagen 1, collagen 10, and so on. The thing is we'll never make something as complicated as the native tissue, but what we're trying to do is what is a cue that we could give them that sort of, signals them, hey, this is bone, this is cartilage, you should become a bone or a cartilage cell, and then let them do the rest. Because we're never going to be able to reproduce the tissue synthetically as well as nature did it the first time. So we're trying to take a more regenerative approach and, push them towards producing the type of tissue that we want them to produce.
Now, is there anything that you can share so far about your results or anything surprising that you and your team have discovered so far?
Yeah, so the coolest thing that we have discovered is that the cells do respond differently when we have the two cues. So remember I talked about presenting biochemical cues that drive it towards cartilage and then another set of biochemical cues that drive it towards bone. We are able to construct a single material that has both of these cues within the same construct. And what's really interesting is that we thought that, having the cues towards cartilage or having the cues towards bone would drive that tissue formation if you had a single material with just one of the cues. But for some reason, the cells are really responding to having both of the cues in the same environment. And we really don't totally know why, but I think that's the exciting part. So we know if we take a scaffold, so this material that we're printing, and we print it with both the cartilage promoting and then the bone promoting biochemical cue, that will produce a more cartilage-like and more bone-like response than if we had them separately in two different scaffolds, which is really not what we expected to have happen. What we think is happening is that these cells are communicating with each other. I liken it to like having a hotel where like the upper floor, the cartilage floor, and the lower floors are bone. And the cells are kind of sending signals back and forth within that single environment that's amplifying the effect. The other thing that we have just now started discovering is that if you take those same biochemical cues that we have split into two different compartments within a single material, if we actually just mix it all up so that you have all the biochemical cues homogeneously presented, both of them, and there's no spatial organization between the two compartments, the cells also respond differently. So they actually need to be separate to get one response. And then if you mix them, they respond differently. And so I think that's pretty cool because it's not enough that you have, this goes back to my analogy about putting things in a blender, right? It's not enough to have the components there. They actually need to be organized in a specific way to get them to produce the type of tissue that you want. So if you mix up that organization, you're going to get a different type of tissue that forms. And I think that's really exciting.
Wow. So what is next then? Where are you now in the research?
So we're finishing up those studies. So we use human stem cell donors, and we are trying to show that it works in multiple donors because that helps us understand how different people will respond. And then our next step is to implant these in vivo in a rabbit model. And that rabbit model will help us understand we're doing everything in culture under very controlled conditions. When you put it into an animal, it's a completely different ballgame. And so we're trying to understand what will happen if we take our scaffold and we implant it inside a defect in an animal.
So further down the road, like what could it mean for my hypothetical self who just very recently, wrecked her cartilage? What could your research look like potentially in my life?
So the dream would be we can make a material that's very simple. It could sit on the shelf at a doctor's office. Somebody comes in with an injury, they remove the damaged cartilage, and then you just implant this material. You can punch it out to the shape that you need for the patient. And then the idea would be that specific scaffold that you implant in the defect site would help your tissue, your native cells, the cells that you already have in your body, to populate that scaffold and then produce a tissue that's exactly the same as your native tissue. So as if you had never had the injury in the first place. As that tissue's forming, your scaffold is dissolving away, and then there'd be no trace at all that anything had even happened, that you'd even had damage in the first place. And that would be amazing, right? So you could have this done in an outpatient procedure, and then instead of you eventually forming osteoarthritis, we would sort of, get to it before you go down that path of where you'll need a total knee replacement. So that's sort of the vision that we have. I mean, it's going to be a long road to get there, but that's really been the dream that a lot of us in the field have been chasing for a long time.
Wow, that's so exciting. Are there other applications, potential applications for your research? Like, could it be applied to burn victims, for example?
Yeah, so what I like about the platform that we've developed is that, I talked about the Lego pieces and these modular building blocks that you can mix and match and change the chemistry. And that's actually sort of by design. We did that on purpose so that we could translate this same technology to other tissues. So as you mentioned, skin is actually a very complicated tissue. It has, again, the same sort of idea that I talked about. It's very well organized. That's very critical for it to function the way that it does. And so we'd like to be able to take our same platform and translate it to saying, helping burn victims regrow that skin without having to have massive skin grafts that can lead to other complications. So having a material that you could print to the size that the patient needs, that has all of those chemical cues that help regrow that tissue, that would be really fantastic.
You mentioned when we spoke previously that you have knee problems and that if you could have had an intervention as a teenager, you might not have a doctor telling you today that you might need a knee replacement in 20 years, which would make you a very young person for something like that. So do you want to say anything about why this line of research is important to you personally and what keeps you motivated?
So I had an injury in my teens. I played soccer and I had a surgery. I had a couple of interventions early on, but knowing what I know now, those interventions were never going to be long-term solutions. And so now I'm in my 30s and I have issues with pain. So going downstairs especially can be particularly uncomfortable sometimes, and I have limitations with what I can do. I will also admit that I am not the most compliant patient. So I was not supposed to be running. I wasn't supposed to continue sports to the extent, but I did anyway. So I'm now at the stage where I have enough pain that I will need an intervention. And the fact I mentioned before about, patients only go in when they have pain. And when they have pain is when they've already lost enough of their tissue. They've had enough damage that it's irreparable at this stage. I know that it's inevitable, and I just don't see any reason why anybody else should have to have that. So the technologies we're developing won't help me. I'm already too far gone. But, when I think about this is especially a problem for women playing sports. So young women playing sports are more likely to have the same injuries that I've had. And if we could intervene earlier, they don't have to face those sorts of issues later in their life. They can have a long, healthy life without having to deal with, mobility issues. And I'm far too young to be having some mobility issues. And so it's only going to get worse from here. And also just the impact that that'll have on our healthcare system. And it also would be an intervention that could be done more widely. So our materials are relatively cheap. You could have an implant done in outpatient procedures. I mean, this is, my dream for it. But I just see something that's much more accessible, something that could be done in a much more affordable way and really decrease the need for just ongoing intervention.
That's it for today's show. Thanks so much to Lesley and to her very patient dog, who you may have heard in the background, for taking time out of a busy semester to share the important work that she and her team are doing. You can read more about Lesley's research in the fall issue of Resolve. It goes online this week, and we'll have links to it on the episode page. For more information about academic programs at the P.C. Rawson College of Engineering and Applied Science, and to find our show, head to engineering.lehigh.edu. Music in this episode is by Blue Dot Sessions. You can subscribe to Rawson Connection wherever you get your shows. And send us story suggestions or feedback on Twitter at Rawson Podcast. Thanks for listening, and stay safe.